Hello, and welcome to the SAC-P4 presentation of Middle and Late Pleistocene Paleoscape modeling along the southern coast of South Africa. Our research team has developed a method to estimate the morphology of the South African coast, spanning the last 430,000 years, using a reconstructed relative sea level curve published by Valbroek et al. In 2002. The South African coast is tectonically stable, so we can use the reconstructed sea level heights as a guide to intersect a level plane across the high-resolution terrestrial and bathymetric digital elevation data. The intersection provides a model of coastline morphology during that specific sea stand and time period. We can then use each of these individual coastline models, spanning the 430,000 year time range of the reconstructed isotopes curve, to measure the distances from the modeled coastline to any number of Middle and Late Pleistocene archaeological sites. Knowing these distances is important because modern ethnographic research has shown that hunter-gatherers will only exploit coastal resources when the coastline is within 5 to 10 kilometers of their home base. There has been prior research on calculating the distance of the coastline to now coastal MSA archaeological sites. However, these studies have all been presented statically and two-dimensionally. Our method differs because it is organic, so we can incorporate new data quickly and easily, and it is also multidimensional, so that we can observe the distribution of the South African coast across space and time within an appropriate three-dimensional setting. The continental shelf along the South African coast is highly variable. Along the east coast, a very narrow shelf opens onto the broad and deep Natal Valley and Transkei Basin. On the west coast, the shallow, gradually sloped Southwest African margin extends around 200 kilometers offshore before dropping onto the Cape Plain. The south coast is dominated by the Agulhas Bank, a broad and relatively flat terrace of submerged land extending nearly 300 kilometers from the current coastline. Because of the unique topography of the South African coast, not all sea level stands are equal. Areas with a narrow and steep continental shelf, such as along the east coast of South Africa, effectively cap the maximum distance of sea levels during regression phases. In a situation like this, even if there is a large change in the mean sea level, the steep topography will prevent large lateral changes in the coastline movement. In contrast, areas with a broad and gradually sloping topography, like the Agulhas Bank or the Southwest African margin, mean that even minor changes in the height of mean sea level can affect vast changes in the lateral movement of the coastline. Initially, we developed our model around Pinnacle Point. As we tested and refined our model, we felt confident that it could be expanded across much of the southern South African coast. When we model the coastlines across the southern South African coast, we find that the broad and nearly flat Agulhas Bank allows for large lateral movements of the coastline through time. What is most interesting about this is that even during periods when the sea levels are well known to be lower, such as marine isotope stage 6, there does appear to be several rapid and very brief sea level transgressions, which brought the coastline within 10 kilometers of Pinnacle Point. The current animation sequence shows the fluctuations in reconstructed sea level heights and coastline morphology from 176,000 to 152,000 years ago during MIS 6. This time is equivalent to the LCMSA lower deposits at PP13b. This sequence represents the effectiveness of our model schema. It is organic, so we can input numerous diverse data sources. It is dynamic, so we can render the data across space and time. And the model is multidimensional, so we can render, view, and analyze our data within a geometric construct more similar to the physical universe in which we live in, rather than just tables and static flat figures. But most importantly for our purposes, our model transcends basic graphics. The digital elevation models, the sea level heights, and even coastlines which are derived from these can each be tested, rejected, or revised. Having now more powerful computers and software, we can use the modern scientific method to test our hypotheses in a way which is engaging and sensible to our perceptions of the real world around us. Our current model is only just the beginning. As we expand our sea levels model and associate it with more climatic, environmental, and archaeological data, we can truly start to model past paleoscapes in our study area, situating the records for human evolution within a dynamic model of paleo-environmental changes.